Hi students, this is Viswanath, chemistry faculty for NEET and IIT exams. In previous classes, we completed Rutherford's atomic model and Bohr's atomic model. Those were proposed based on classical mechanics. Classical mechanics was developed based on Newton's laws. These Newton's laws are applicable only for microscopic objects like planets and moving car and moving ball like that. But for microscopic objects like electron, proton, neutron, atom and molecule, for these species, these Newton's laws were not applicable. That's why another model of atom were proposed based on quantum mechanics. This quantum mechanics was developed based on Schrodinger wave equation. Schrodinger wave equation is dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square into e minus v into psi equal to 0. This is Schrodinger wave equation. Based upon this, quantum mechanics was developed. The derivation of this Schrodinger wave equation and solutions of this Schrodinger wave equation you will learn in post-graduation level. At this +1 level, just remember this equation. Okay. So based upon this quantum mechanics, we can define what is orbital, what is the energy of orbital, what is the size of the radius, everything we can get. Now say this. Shapes of atomic orbitals. What are the shapes of atomic orbitals? Before that, what is atomic orbital? See, the space around the nucleus of an atom in which there is a maximum probability of finding an electron is called an orbital. So inside the atom at the center, nucleus is present. Around the nucleus, electrons are revolving. That means after proposal of Heisenberg uncertainty principle, definite path for electron rotation is not possible. What we can find? A three-dimensional path around the nucleus we can find. So that is called orbital. That means at which place most of the time electron is present around the nucleus, that space is called atomic orbital. I give a simple example for your understanding. In school, most of the time students are spending in classroom. They may spend some time in corridor and playground and library and laboratory. But most of the time they will spend in classroom. So for students, classroom is the atomic orbital. In the same way, around the nucleus, inside the atom, most of the time electron is present in a particular place. That space is called atomic orbital. So definition, the space around the nucleus of an atom in which there is maximum probability of finding an electron. So more than 90% of possibility is there in a particular place. That place is called atomic orbital. Now say this electron cloud distribution diagrams of 1s, 2s and 3s orbitals. Say this for 1s orbital, this plus symbol indicates nucleus of the atom. Around this, these dots represent possible places for electron existence. In these places, at particular place electron is present. That means electron is revolving with very high speed around the nucleus. At this particular instant, electron is present here. In the next instant, it may be there. Next, it may be there. Next, it may be there. If we join all these possible places, then we can get this type of shape. Okay. All these possible places are simply called electron cloud. This is for 1s orbital. Next, 2s orbital. This is nucleus. These positions represent electron possible places. Again, some gap is there. In this gap, we cannot find the existence of electron. Again, in these places, in these gaps, these dots represent possibility of existing of electron. This is for 2s orbital. And so this is electron cloud and this one also electron cloud. Next, for 3s orbital, this is nucleus. These places represent electron cloud. Electron possibility, here also electron possibility, this one also electron possibility. This gap represents no electron existence. Here also electron does not exist at this place. So this is electron cloud, this and this also electron clouds, and this is called node, this one also called node, and this is also called node. This at this place where electron density becomes 0, probability of finding electron density is 0, that is called node. See this node definition. Node, the region where electron probability density psi square is 0 is called node. At a particular place around the nucleus, electron probability density, we cannot find the electron in that particular place, that is called node. These nodes are two types, radial nodes or spherical nodes. Next one is angular or nodal planes. Say this radial or spherical nodes, it is a three-dimensional space around the nucleus where probability density of electron is 0. Around the nucleus in a three-dimensional space or at a particular point, electron density, probability density of electron is 0, that is called radial node. It is also called spherical node. It can be calculated by n minus L minus 1. Already we completed quantum numbers, n principal quantum number, L azimuthal quantum number. Okay, now for 1s orbital radial nodes, how much? Substitute n and L value. Principal quantum number n, for s orbital azimuthal quantum number value 0, n 1 minus 0 minus 1, that equal to 0. For 2s orbital, according to this, 1 radial node. 3s orbital, 2 radial nodes. For 2p orbital 0, 3p orbital 1, 4p. Next 3d orbital radial nodes 0, 4d 1, 5d 2. See this 3d orbital principal quantum number 3. For d orbital L value 2. 3 minus 2 minus 1, total 0. In this way, for s, p, d, f orbitals we can find radial nodes. In case of f orbital, according to this formula, suppose 4f orbital is there. How many radial nodes are possible? 4 minus L value 3 minus 1, 0. So for 4f orbital, number of radial nodes are 0. 5f orbital 1. Like this, we can calculate radial nodes for various types of atomic orbitals. Simply remember, radial node means the point or three-dimensional space around the nucleus where probability of electron density is 0, that is called radial node. See the next one. Angular node. Angular node means, say this, the plane in which probability of finding electron density 0 is called angular node. It is a two-dimensional region. Along two axes, a plane is formed. In that plane, electron density is 0, that is angular node. It is also called nodal plane. It can be calculated by L value. Based on L value, we can say number of angular nodes. For 1s orbital, angular nodes 0, because s orbital, whatever the s orbital, whether it is 1s, 2s, 4s, 5s, any s orbital, L value is same, that is 0. So angular nodes 0. So 2p orbital, angular nodes 1, because for any p orbital, 2p, 3p, 4p, whatever the p orbital, L value 1. So angular nodes 1. That means nodal planes are 1. For s orbital, nodal planes are 0. For d orbital, nodal planes are 2. Because d orbital, L value 2, nodal planes 3d, 4d, 5d, whatever it is, nodal planes are 2. For 4f orbital, angular nodes are 3. Because for f orbital, nodal planes L value 3, so nodal planes are 3. Next, see the important points. For s orbital, the probability of finding the electron at a given distance is equal in all the directions. That means around the nucleus, if we find probability of finding electron is equal in all the directions along x and y and z axis. That means there is no nodal plane or angular node for s orbital. Therefore, all the s orbitals are spherically symmetric. So, from these nodal planes, we can find shape of the atomic orbitals. For s orbital, we can find equal probability of electron density along xyz axis. That's why the shape of s orbital is spherical. Okay, so shape of s orbital is spherical and it is symmetrical in the structure. it is a non-directional. Remember that s orbital is a non-directional in nature. And second point, the size of the s orbital increases with increase in principal quantum number. Principal quantum number increases, then s orbital size also increases. So compare 1s, 2s, 3s, 4s. Size increases, then energy also increases. So the order of size and energy of s orbitals is 4s greater than 3s greater than 2s greater than 1s. 1s orbital size is small, having less energy. 4s orbital size is bigger, having more energy. Okay. Next, p orbital. For p orbital, each p orbital consists of two lobes that are on either side of the plane that passes through the nucleus. Through the nucleus, a plane is passing. In that plane, no electron density. On either side of this plane, two lobes are there. The probability density function is 0 on this plane where the two lobes touch each other. See the diagram, you can understand easily. This is one lobe, another lobe. These two are touching at this point. At this point indicates nucleus. A plane passing through this nucleus, it has no electron density. Okay, plane passing through the nucleus has no electron density. On either side of the plane, two lobes are there. This lobe represents electron density. This one also represents electron density. Next, the size, shape and energy of three p orbitals are identical. P orbitals are direction in nature. Px, Py, Pz. Along x, y, z axis, these orbitals are arranged. That means electron density is present along the axis. Say this. They differ in the way the lobes are oriented, means lobes are arranged. Since the lobes may be considered to lie along xyz axis, they are represented px, py, pz. Px, electron density is present. That means lobes are present along x-axis, py, along y-axis, pz, along z-axis. Here we consider this is py. Py orbital, electron density is present along y-axis. No electron density along x and z-axis. Okay. Next. So the shape of all p orbitals have dumbbell shape. These electron density shape is dumbbell shape. Remember, s orbital is spherical, p orbital is dumbbell. Next, like s orbitals, the size and energy of p orbitals increase with increase in the principal quantum number. N value increases, then size and energy of p orbitals also increases just like s orbitals. Hence, the order of energy and size of the various p orbitals, 4p greater than 2p 3p greater than 2p. That means 2p orbital size is less, energy is less, and 4p orbital size is more, and energy is also high. Okay. Next, for px orbital, angular node. For p orbital, L value equal to 1, so angular node is 1. What is the nodal plane? YZ plane. In this plane, no electron density for this orbital. For py orbital, Zx is the nodal plane, Pz orbital, Xy is the nodal plane. Each p orbital having one nodal plane, those are these. Next, for L equal to 2, we have 5 d orbitals and are designated as dxy, dyz, dxz, dx square, y square, dz square. Remember, some students can call this as dx square minus y square, but that is wrong. This is not minus, this is hyphen. Dx square, y square. The shapes of first 4 d orbitals are similar. First 4 means these 4 orbitals having same type of shapes. Dz square orbital shape is different. Say this, that means all these 4 d orbitals have 4 lobes each one, and dz square orbital has 2 lobes and a concentric ring having electron density around the nucleus. First 4 d orbitals have 4 lobes and dz square orbital has only 2 lobes. Around the nucleus, concentric electron density is present. Okay, but all the d orbitals have equivalent in energy. Their shapes may be different, but they have same energy, equivalent energy. The size and energy of d orbitals increase with increase in principal quantum number. Same, s orbital, p orbital and d orbital also principal quantum number increases. Their shape and energy increases. Next, all the d orbitals except dz square have two nodal planes. Come to the nodal planes. Except these remaining four d orbitals dxy, dyz, dxz, dx square, y square. These four orbitals have two nodal planes each one. But dz square has no nodal planes. Actually, it has nodal cones. Two nodal cones are there. It has two nodal cones. So for these orbitals, electron density is present in between the axes. Dx square, y square electron density is along x and y axis. For dz square orbital, electron density is along z axis. The shapes of all d orbitals except this are double dumbbell. Remember that dxy, dyz, dxz, dx square, y square orbitals shape is double dumbbell. Okay, except dz square. For these three orbitals, electron density is in between the axes. Suppose dxy means electron density is present between x and y axis. Here also similar to that one. Next, dx square y square means electron density is along x axis and y axis. Here along z axis. See the nodal planes for dxy orbital. Nodal planes equal to 2. What are those? Yz plane, zx plane. In these planes, no electron density. For dyz orbital, nodal planes zx, xy, dxz, nodal planes xy, yz, dx square, y square, yz, zx. Okay. How can we remember? That is your doubt. These nodal planes. Say this dxy orbital. What are the remaining? What is the remaining axis? Z. So xz, yz are nodal planes. dyz orbital. What is the remaining axis? X axis. So xy, zx nodal planes. dxz. What is the remaining axis? Y. So xy, yz nodal plane. dx square, y square. What is the remaining axis? Z axis. So yz, zx are nodal planes. Okay. Next. In case of dz square orbital, there are two nodal cones instead of nodal planes because there are no perfect planes, but according to the orbital orientation, orbital arrangement, we can represent the nodal cones. It has zero nodal planes but has two nodal cones. These nodal cones are also called conical nodes. Okay. For this dz square orbital, remember carefully, two nodal cones are there, no nodal planes. Okay. Next, see the conclusion. When the number of nodal plane increases, the energy of the orbital increases. So the energy order of orbitals is S less than P less than D less than F. So for F orbital, more nodal planes than D, P and S. S orbital having zero nodal planes. Number of radial nodes n minus L minus 1. Number of angular nodes L. By combining these two, we can get a total number of nodes. Formula n minus 1. Remember this formula. Based on this, multiple choice questions will come. Practice well. We will meet in the next class.